So we have the idea of the complex plane, where this is the real part of a complex number, mapped onto the x-axis, and the imaginary part mapped onto the y-axis. And I can pick a point, and because I'm uncreative, I will just put that point in the first quadrant. So this is the x value, this is the y value, and we have two ways of representing complex numbers. So we can use rectangular form, which is to say z equals x plus iy. Or alternately, we can kind of undo the Euler formula, and we can describe a complex number by rho and theta. Let's use theta. Or that equals r ei phi. And the correspondence in between the two, of course, is Euler's formula, which is r cosine theta plus I r sine theta. So this would be y and this would be x. So just the usual thing we've been doing. Okay, so now we're going to talk about functions of complex variables. So I'm going to take a function f and I'm just going to feed complex numbers into it. And there's no limit on anything you can write down. If you like tangent of x, why not just call it tangent of z? So obviously that's going to be more difficult because z is now a complex number. And we can talk about things like doing calculus on this. But the point is we're now talking about a class of functions. F maps complex numbers to complex numbers. So the first thing to do is introduce a little bit of terminology. And we can think about f of z in rectangular form. And what you're really doing when you feed in a complex number to a function is you're feeding in a real part and an imaginary part, and they can be independently chosen. So it's not exactly true to call this a function of r squared to r squared, but it does have two inputs, two independent inputs. And likewise, the output is also a real and an imaginary part. And so it's traditional and useful to split up complex valued functions into forms that look like this, where the output of the function also has a real part and it also has an imaginary part. So this would be the real part of f of z, and this would be the imaginary part of f of z. Right, and as usual, z is equal to x plus iy here. Okay, so there's no case where you can't do that, right? Because we're mapping, ultimately, a complex number goes in, a complex number goes out. We can always talk about both the input and the output as the real part and the imaginary part of those things. So the first question you can ask, maybe it's not the first question you want to ask, and I'll just say we're not going to talk about it, but there is all sorts of neat and useful stuff you can do with integrals of complex valued functions. So Cauchy's integral theorem, for instance, lets you solve some really interesting and difficult problems in physics, with so-called Green's functions. Their applications to electromagnetic theory and field theory. But we'll satisfy ourselves with just talking about this stuff. It's enough. So you could just say, like, okay, I imagine that if I have a well-behaved enough function, I can talk about its rate of change with respect to the complex variable. The problem is that this thing in the denominator is, complex. And it's not obvious that, for instance, if I have f of z equals z squared, what do you guys really want that to be? And I really hope you're right, but again, it's not obvious. So it would be great if that was equal to 2z, right? Just the derivative of z squared is 2z. But if you're thinking about like, well, what is z squared? Because what I'm going to do is I'm going to multiply, you know, in that second term of the expansion, I'm going to have iy times iy, and all of a sudden that turns into negative y squared. So there's this weird twisting in between the real parts and the imaginary parts where, you know, sort of complicated stuff is going on. And it's not necessarily true that this is the case. So the problem is this thing has a stronger condition on it to exist. So it turns out this is true. It's what you want. However, it's much less frequently well-defined, because a well-defined integral, let's just think about a single variable real function. So I have g of x equals y. And I can certainly come up with some cases where the derivative of g of x at some x naught doesn't exist, right? Like, you know, you don't really have to think too hard. I could just like sketch something. So I could have, you know, a piecewise defined function, of course, doesn't really satisfy this. So dg dx evaluated at x equals x naught doesn't exist because the left limit and the right limit are different. So that's what, you know, the usual meaning of not having a well-defined derivative. That's what we're talking about here. What's the problem with porting this into the complex plane? And it's even going to be hard to draw. So here's some point z naught, and here's the real axis, and here's the imaginary axis. I'm not changing anything up. So here I have to check two conditions to see if the derivative exists. I have to see if the rate of change of the function as I approach x naught from the left and as I approach x naught from the right are equal to the same value. And in this case, that's not true. How many directions do I have to approach z naught from if I'm trying to figure out if df dz exists at z naught? So I could approach from here, 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 here. I could approach from there. I could approach from there. Uh-oh. So there's an infinite number of ways of taking this limit. And I need to check that all infinity of them exist in order to say the derivative exists. And there are definitely pathologies. So if you have like f of z is the natural log of z, there are going to be an infinite number of different answers that you can get at certain points. So this is not good, right? So this in and of itself looks like a really awful problem. And, you know, maybe we give up and we say like, we can never say that a derivative of a complex function exists. So fortunately, some work was done, and, you know, again, more detail in the recorded lectures. But we have this result. Call it the Cauchy-Riemann theorem or the Cauchy-Riemann equations. And they say, oops. A function has a derivative that exists. We call that the function being analytic. It's just terminology. And this should kind of smell a bit familiar because we had a problem like this when we were talking about conservative vector fields, right? We had this issue where you have to check all possible paths from A to B and see if the work done by the force field is the same. And all of a sudden we were able to transmute that condition into a differential statement. We just say like, dude, you don't have to check all paths. All you have to do is see if the curl vanishes on that region. So this is kind of like that, but you know, the style of the proof actually turns out to be the same, but it's not exactly the same because now we're talking about a complex valued function. So we won't prove the Cauchy-Riemann equations, but you should definitely know they exist. So again, U and V are the real and imaginary parts of the complex function. And these are the Cauchy-Riemann conditions. Oops. I'll put the minus sign there, which is good enough. And notice that it kind of does actually look a little bit like a curl vanishing because you're actually equating the mixed partials du with respect to x versus dy with respect to y. So it is really the same sort of proof. Okay. So everybody okay with that so far? Good. So if you have internalized all of that, this should be an easy question. And by easy, maybe takes 5 minutes of work. So what is it that I first need to do to use the Cauchy-Riemann conditions to see if this thing has derivatives and they exist? Because again, what I really want to do is just say like df dz is equal to E of z, which is true. Kind of ruin the answer. But first step in doing this would be what?
We don't know what the functions u or v are.
Exactly.
So
yeah, step one is to work out what u and v are. And to do that, just remember that z equals x plus iy. And remember Euler's equation, and a little bit of algebra should get you there. So first put it in the form f of z equals u of x and y plus I v of x and y as sort of shorthand. And then once you find u and v, then you can check the Cauchy-Riemann conditions. So I'll give you guys 5 minutes to work on that or so. Okay. Everybody have u and v? So this should be as easy as just kind of grinding it out. I have f of z is equal to E of z, and then z is x plus iy. And then I know properties of exponentials. So I have E of x, E of iy. And then the second term, I can use Euler's formula. So I have E of x times cosine of y plus I sine of y. And that's how I get my I stuff out. And finally, splitting that into the real and imaginary parts, I get E of x cosine of y plus I E of x sine of y. So that's u of x and y, and that is v of x and y. So I have u of x and y is equal to ex cosine of y, and I have v of x and y is equal to e to the x sine y. So just as a note, You probably noticed it, but just to be super clear, both of these are real valued functions. The complexness is just the I is pulled all the way out in front of V. So essentially what these are both U and V separately are functions that take R2 to R, right? So two real numbers, and then it spits out just one real number. Okay, so once we have these, we can apply the Cauchy-Riemann equations. So any questions about where those came from first? Okay. So now we can use the Cauchy-Riemann equations. And I can look at du dx, and du dx is e to the x cosine of y. And I can look at d partial v with respect to y. And partial v with respect to y is e to the x cosine of y. So we do have something interesting to integrate there. And these two things are equal. So that Cauchy-Riemann equation is satisfied. And then likewise, I can look at minus du partial u with respect to y. And minus partial u with respect to y is minus e to the x minus sine y. And partial v with respect to x is equal to ex sine y. So ta-da, again. So everywhere. So our conclusion from this is that, oops. Yes, our conclusion is a bright green check mark. The conclusion is that f of z equals e to the z is analytic everywhere. And there are about 3 examples in the video of things that are analytic some places, but not other places. And one that's analytic nowhere but one point, even though you would think that it's, you know, perfectly regular function. The interesting thing about the modulus squared function in that example is that if you think about the absolute value in just 1D, like absolute value of x, that's a function that's differentiable everywhere but 0. Its complex version is differentiable nowhere but 0. So I always thought that was like kind of cool. So any questions about that? So that's what it means, and this is the condition that you check to just see if you can take a differentiable function. And this will be really important because if you can tell me a differentiable complex valued function, I can give you one solution of Laplace's equation from another one. So we do need this. It's good. Okay. So a little bit more background. We've got a couple of results. And stated really briefly, this is the one that gets us to Laplace's equation. So one result is that if f is analytic, then, so remember this is not obvious. I mean, you can come up with stuff that's continuous but doesn't have a derivative, that's continuous as a first derivative but no second derivative. This is actually a much weaker statement of the full theorem, is that if f is analytic, actually all derivatives exist. But this is the one that we care about. So if a function is analytic, it turns out that the component functions, the real and the imaginary components, solve Laplace's equation. So this is pretty great. And there's a corollary of that. You could call this like the physicist corollary, is that if you have some g, I don't know, just, oops, g of x and y. Give me a 2D function, and that 2D function satisfies Laplace's equation, then there exists some h of x and y, which together make an analytic function. So any solution of Laplace's equation could be the real part or the imaginary part, it's up to you, of an analytic function. And these two things are called harmonic conjugates. And the way that this would work is that if you know G, or really if you know one harmonic conjugate, which I'll just start calling HC, the Cauchy-Riemann conditions will get you the other one. Okay, so this is a little bit steeper, but I'll just give you guys some time to work on this too. Because this, again, the tools that you have to solve these, they're basically the things that we talked about when we were talking about conservative vector fields and potential functions. So the idea of undoing partial derivatives will show up in this problem. So if you can do this, we're ready to just go on to conformal mapping. So this is all the background. And I'll tell you it's going to be the real part of the function. So I'll just say that this is u of x and y. Okay, so I give you u of x and y equal to x cubed minus 3xy squared. And I'm telling you that it's one of the harmonic conjugates of some analytic function. So you should be able to find v of x and y. And then with a little bit of squinting, so you don't have to prove it, you can just guess what it is and you'll be right, and we'll show that. This is something that can be written as just a function f of z. So only the variable z appears, which is another way of thinking about analytic functions. Okay, so just use the Cauchy-Riemann conditions. So partial u with respect to x is equal to 3x squared minus 3y squared. And that equals partial v with respect to y. So that means that if I undo the partial derivative with respect to y, we get 3x squared y minus y cubed. But then because, if you remember the discussion when we talked about potential functions, I'm taking a partial derivative with respect to y. So that means there's some unknown function, we'll call it h and it's got to be a function of x only. So any function of x only would have been destroyed by the partial derivative with respect to y. So this is equal to v of x and y. But then we have the second condition, which is negative partial u with respect to y. So taking that, I get 6xy, and that equals partial v with respect to x. And undoing that, what I get is 3x squared y plus some unknown function, call it g. And that could be an unknown function of y, which would have been destroyed by the partial derivative with respect to x. And so that also equals v of x and y. So now we do the comparison. First term looks good. What must g of y be? So just by comparing these terms, g of y needs to be negative y cubed. And then h of x could be a constant, a constant because we're going to be talking about potentials ultimately. You can add a constant to a potential energy function and it doesn't matter because the real physical thing is a force and you get the force by taking a derivative. So ultimately constants won't matter. And honestly, you could put in a constant in a complex number there and it still wouldn't change anything. So ultimately we have v of x and y has got to be equal to 3x squared y minus y cubed. And that means the function of z, which is a function of x and y, which is u plus iv, is the thing that we were given, x cubed minus 3xy squared, plus I 3x squared y minus y cubed. Okay, any progress or intuition or guesses as to what this might look like? Maybe just based on like powers and stuff?
I worked it out to be z cubed.
It is z cubed, right? And z cubed gets hidden because I is I, and I squared is -1, and I cubed is equal to minus I. And so the minus I here with the cubed, and then this mixed term gets split up. So the mixed terms that have the x's end up with an I, and the mixed terms that have y squareds end up with a minus sign. So it is z cubed, it's just kind of hidden in a funky way. And you can see Pascal's triangle and the coefficients. You know, there's 1, there's 3, there's 3, there's 1. Sneaky, sneaky. So yeah, you guys worked really hard to find z cubed. Isn't complex analysis great? Okay, so this is the last theorem, and this is our launching point to, the payoff of you guys just like dreaming up crazy functions and seeing what they happen to do to stuff. So last theorem. So that is part is a little bit of a softer condition, but that's the part that we care about. So analytic functions provide conformal mappings, which means if you have a plot or you have a contour of 2 lines in the complex plane. So I have one line, contour 1, and I have a second contour, contour 2. and they have some angle in between them. And this is the z-plane. So you just draw two lines in the complex plane. And I take any analytic function whatsoever. This angle is going to be the same after I take the, after I pump it through the analytic function. I mean, this, you know, the more you think about that, the crazier it seems, but I'll show you guys some examples. So the way that you can think about this in a sense is take a piece of rubber, draw a bunch of straight lines on it that intersect at right angles, and then analytic functions can, in a sense, be defined as ways of stretching the rubber that preserve the angles locally. So they always intersect at 90-degree angles if they started in 90-degree angles. So specifically, in the really important case, and this is what we'll do most of the time. So I have z equals x plus iy. So lines of constant x and y is constant. They're perpendicular, right? We have an orthogonal coordinate system. So that means that lines of constant x, lines in constant y being perpendicular before I apply some analytic function means that afterwards, lines of constant u and v are perpendicular in the after image of the image of the function. So the way this is going to work in practice is that we're going to make a so-called complex potential with the actual potential we care about, a solution of Laplace's equation. We're going to add something to the imaginary side and then just try a function, see what happens. So let me, I think this is probably the appropriate time to talk about physics. So this is a big set of applications. Is that this is what, for instance, the voltage in between two parallel plates of parallel plate capacitor looks like. Maybe this is 10 volts and maybe this is 0 volts when it hits the other plate. So these are the equipotential lines. And then the electric field lines would run like this. And this is just ready to go right into this whole conformal mapping scheme. So these are the electric field lines. The electric field lines are perpendicular to the lines of equipotential. So this is very much shorthand for that. Like electric field lines are electric field lines. They're not necessarily the electric fields in general, but this is true in this case of a parallel plate capacitor. So the equipotentials are perpendicular to the electric field lines. So what I could do is I could just call these x. They really look like x to me. And I could call these y. And then I could note that if I have z equals x plus iy, and I also have, so says physics, I have in a region without charge, the potential of the electric potential satisfies Laplace's equation. So del squared phi is 0. So this means that it very well could be the one or the other parts of f of z equals u plus iv, right? So the program is as follows. It's written out really nice. And this would work with gravity and it would work with ideal fluids as well. So this is our conformal mapping program. So it turns out that you don't necessarily have to associate so we'll call this just phi plus I psi. You can put the potential into the real part, or you can put the potential into the imaginary part. It doesn't matter as long as they're harmonic conjugates. Usually the easy case is just Z, because it's very much true that this is true. I'll show you another case that's easy in a second. And then really just come up with f of z. And then what you have guaranteed is that del squared u equals del squared v equals 0. So that these two things are also solutions of the Laplace equation. So that's what we've been talking about. Okay, let me give an example, both show it and work through the background. Can you guys see the Mathematica screen? Okay. So this could be equipotentials, or this could be electric field lines, or this could be the streamlines of fluid flow. Like think about those, the lines of smoke in a wind tunnel. So that could be any of these. And I have F and a G, so those would be my U and V, probably would be a better way of describing them to be consistent about the notation. And essentially what I'm doing is I'm taking this, and you guys now recognize exponential x cosine, exponential x cosine. I'll explain the y over 2 in a second. It's just so we map only half of it. We don't want the whole thing. So we've actually shown that this is an analytic function already, so I get that for free. And it's got a little coefficient on it, so I'm going to start changing the coefficient, get it up to 0.1 first, and see what happens. So what do you guys know about, notice about the lines of constant whatever? I ratchet it up to 0.2. I ratchet it up to 0.5. So this could be two things to me, just qualitatively. This could be like streamlines, so the flow of fluid, a steady state fluid flow that's leaving the end of a pipe, right? So the pipe could be here, and then this is the end of the pipe. This could be something from electrostatics too, that we just solved and you were told never to worry about in electrostatics. So these could be the equipotential lines of something that's no longer infinitely big. So what do you think the equipotentials look like of a parallel plate capacitor as you get to the end of the parallel plates? So they're actually going to do something like this, right? So an infinite parallel plate capacitor, all the equipotentials are evenly spaced and straight lines. But as you get to the end of it, in fact, and I know that this is the answer because it solves Laplace's equation, right? So just anything I can come up with will solve Laplace's equation. And in a sense, what's happening by controlling this parameter, let me make it really big and you'll see some funky stuff happen. So basically controlling maybe like how strong how much charge is on the plates, so the total voltage, right? Or maybe the dielectric constant in between it or something like that. So, you know, this is neat because it's exactly backwards from how we usually do physics, where it's like somebody describes the situation and then you work really hard to get the answer. I just know this is the answer to some electrostatics problem, and then I'd have to like work backwards and figure out what I actually just solved. And I'm limited only by my ability to type in numbers. Okay, so I'll show this with a couple of other transformations, and then we'll work on a little bit of how you would do this in practice. Okay, so again, I'm starting with X and Y, and I'm plotting the constant lines of, in this case, clearly constant lines of Y. And then I have another thing that I can show to be an analytic function, and then I'm going to kind of ratchet it up. And you guys can tell me what you think this might be. So what do you suppose that is? And I think there are two pretty good answers, three if you believe in antimatter, I guess. So first one, maybe think about wind tunnel. So you can imagine that this is a golf ball in a wind tunnel at really slow wind speed, right? So this is how the wind would go around the golf ball. The other thing that this could be is a charged thingy in an external electric field, right? Where the field lines bend around it. Maybe. Okay, and then I'll show one more. So these are my initial lines. So this one's actually kind of harder to do. So to comment stuff out. And this is x squared. So if you stare at f and g, maybe you can now convince yourself that this is x squared. So I have an I squared that gives me a negative y. I get an x squared from an x squared. And then the mixed term that remains imaginary is 2xy. So I x squared something, and then what I do is I end up bending these lines around. So in this case, maybe you could imagine wind going into, you know, the dead end of an alley or something like that, or electric field lines being deflected by a charge plate of the same charge. Okay, so this is, again, really nice because I know these are all solutions of Laplace's equation. Now I just got to, like, you know, fish for a way of making people care about them. So any questions about that? Okay, the neat parametric plot, I'll just explain what it is and give you guys this template code if you want to use it to solve the Yukovsky problem. So that's an airfoil. So I'll just show what that is really quickly. So this is, it's evaluating x and y, but it's using y as a table. So integer spaced values in between -6 and 6. And then x is plotted continuously in between these. So I can change this to plot it from, you know, -10 to 5 or something like that. And you can see these things really fly around, right? So this is the fluid coming out of the pipe and then flying all over the place. So there's maybe a limit as to how, you know, useful that is. -8 and 2 will probably get us back to normalcy. All right, so that looks more like our fluid flow in a pipe. Okay. So this is the wind tunnel stuff. So these are what are called smoke lifts, where you have, I think it's some weird, it's like titanium oxide powder, really fine powder that they just inject into the streams. And it turns out for an ideal fluid, this is not an ideal fluid. I already kind of see the onset of turbulence, and I know it's got some viscosity, but, you know, honestly good enough that this actually is solved by Laplace's equation too. So these are what are called the streamlines. And so that's the airfoil thing that I gave you guys for the homework. So it turns out you can solve not the turbulent part, but you can solve these problems now.